So welcome to Group 2 Alkaline Earth Metals, okay, in the first year of this course. Usually, let's just start going through it straight away. S block. So first of all, they are S block, which means part of your periodic table. So if you look down the Group 2, they are in the S block section. So they all have 2 electrons in that S block. Okay, so that's why I've written S to the 2, because normally you do 1s2 and the 2 goes up to the top, or 2s2, and we'll show you that in a minute. And they're lost. Those 2 electrons are lost to form 2+ ions. So if you look here, here are all of the S block electrons that we have got, and we can see all of these are in the S block. So when they form ions, these S block electrons all just do this, and they disappear and they go away. And you can see here we've written the noble gases. Now that just means they have the electron configuration of that noble gas. So the electron configuration of that noble gas is 1s2. So if I go back, that would be 1s2, 2s2. Okay, so that's all that means. But we're talking about the ions. The ions form 2+ ions, and because of the loss of that S block electrons. Now they're in the S block because the highest energy electron that they have is in the S block, and that's a common question as well. So the reactivity is based upon atomic size. Now that means down the group they have more shells. Because they have more shells, they're more shielding, although the word shielding doesn't really get used too much in your A-levels anymore. It's more of a GCSE word. Okay, and you can see here, as I've got my lovely pictures, you can see it's getting bigger as it goes down. So if I bend down a little bit here and I just go, you can see as you go down. So as we go down, there's a lower attraction between the outer electron and the nucleus. Okay, that's because you've got all those shells in the way. And again, we only tell you the things you need for the exams. So these are the words you need for the exams. And it takes less energy. Now in GCSE, it was more easily. Now it's energy related, so it takes less energy to remove that outer electron, okay? And so when they react by losing the outer electrons. So that's why we're talking about losing the outer electron and why it's easier to lose the outer electron as you go down, and linking that into reactivity. Now, that is the same as ionization energy, really, on the first and the second ionization energy. So energy required to remove an electron from each atom in the gaseous state to form 1 mole of gaseous 1+ ions. That's our definition of ionization energy. And you've got the same answer down the group. They have more shells, more shielding, okay, lower attraction between the outer electron and the nucleus, and takes less energy to remove them. So that basically means, as you go down here, your first ionization energy, the amount of energy it takes to remove an electron from each atom is going to get less because you've got more shells and the attraction is lower. But that is your exam answer. So now we're going to compare the reactivity of Group 1 versus Group 2. Now across the period, the radius of the atom decreases, and that's due to increased nuclear charge. Now what does nuclear charge mean? Nuclear charge means that there's more protons. Okay? Protons are positive and they hold the electrons in place because they're negative. And because there's more protons, it pulls the electrons in just ever so slightly. Okay? So it pulls those electrons in ever so slightly. So what you get is in Group 1, which is sodium, you can see that this is larger than the magnesium. Okay, that's because the magnesium is in Group 2 and then sodium is in Group 1. Now, that means the attraction for the outer electron increases as you go from Group 1 to Group 2. Okay, now if the attraction for the outer electrons increase, okay, that affects the reactivity. So if you think of a reaction like this, sodium plus chlorine goes to sodium chloride. For the sodium to react with chlorine, it has to turn into Na+. This is ionic, and it has to turn into Na+, and the Cl has to turn into Cl-. We're only talking about the metal at the moment. But to do that, it needs to do this. It needs to lose an electron, and that is your ionization energy. Okay, so if you want to look at reactivity, a good way of looking at reactivity is to look at how much energy it takes to ionize it. Okay, so the reactivity decreases from Group 1 to Group 2, and that's because the first ionization energy is higher in Group 2, and that's because of the reduced radius, okay, which is because of the nuclear charge, okay, compared to Group 1. So we should see a less reactive metal in Group 2 compared to in the same period. Remember, we're only comparing in the same period, okay, we're not comparing other periods. Same period, the Group 2 should be less reactive than the Group 1. So we're now going to look at reactions of group 2, and we'll look at some comparisons between group 1 and group 2 as well during this. You see we've got two reactions that are happening here. The reaction we're doing is reacting with oxygen. So the metal is reacting with the oxygen to make the metal oxide, and here's an example of calcium, one of our group 2 metals. And if we look here, and when we start looking at the actual videos, you can see one is calcium. That's a bit of impurity, that green, that's a little bit of copper left on that tongs, okay, so don't worry about that. But let's look at this one, that's really important. The magnesium is burning straight away, really bright white light, one you can't look at when you're in the lab. It's a really cool thing to do as well. And then we've got the calcium, which is taking a bit longer. It shouldn't take a bit longer because it's more reactive, right? But the reason is because it's got an oxide layer around the outside. It's just taking a bit to get through that oxide layer. But when you do get through that oxide layer, it does something like that. I never you saw, but it exploded. And the person filming it went, ah! Right? Okay, and you can see a bit of it there is still left on the tongs, okay? Thank you to our technician Paul for that. So yeah, that was him filming. Now, if we then look at this, these are the reactions that you can do, okay? And let's go to another reaction. So we've done the oxidation, and let's go to the next one. So this one is also in the lab, that's my finger there, okay? And let's have a look at the reactions themselves. So we've got metal plus water goes to metal hydroxide plus hydrogen, okay? I'm going to talk about the observations that you can see in that as well. Calcium as an example, okay? And then hydrochloric acid to react the metal with, and again, calcium as an example. We then go on to this video here. So we're going to go on to the video, and I'm going to try and get out of the way. So first of all, you can see I'm pointing at this. So let's start the video. That's because it's in oil to protect it. And that's sodium in oil, protecting it from the air. This is magnesium, not as reactive, you can see, because it doesn't need the oil, right? Then it's bendy, and you can collapse it, and then we can see the sodium is really, really soft. So you see we look down on it now, and we can see that if we look down on it, that's really, really soft and it's flattened, okay? That's how soft sodium is. We then throw them in water, and you can see that the sodium is bouncing around, okay? And your observations for this would be, I see it moving around, I see it bubbling, fizzing, okay? And eventually you see it disappear, all right? Whereas the magnesium is doing nothing, okay? It's not really reacting. You'd have to heat everything up to make it react with water. You can, but you've got to heat everything up. Next thing is acid. So look at how it's going with the acid. So that's going mental. It's going all over the place, right? This is also going, it's going really bad. You can see the steam coming off here. You see the steam coming off here. So that basically means that because the acid is more reactive, it will react with the magnesium, okay? So that's why you see the magnesium now reacting straight away. The only way you can get a group 2 to react with water is if you heat it up or you leave it in there for a very, 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 very long time, okay? And you can see the magnesium is still going there, okay? And still going around, and you can just about, can't see the steam at the moment, okay? But you can just about see that it's finished, okay? And these are your two reactions, water and with acid. Now remember, that could be with sulfuric acid as well, and it can be with nitric. So a good thing to do would be practice writing out the equations for nitric and sulfuric. Right, let's look at the trend in reactivity. Okay, group 2 oxides, okay, metal oxides can be added to water and they're solubilized to different extents. So I call this a trend in reactivity, but it's really about the hydroxides, because when you either add the metal into water and heat it up, you will get the metal hydroxide. Or you can add the metal oxide to water and it will solubilize and it will make the metal hydroxide. Okay, but when we're talking about reactivity, what we're really talking about is how soluble that metal hydroxide is, because the reactivity is based upon how much of a hydroxide this is. So the more alkaline something is, the more reactive it is. So the more acidic something is, the more reactive it is. So with hydroxides, it's how much more reactive this metal hydroxide is. Now for it to be reactive, we've got to start breaking the bond here. And that's what we're going to talk about. So the most soluble and therefore the most alkaline are at the bottom of the group. That's all you need to know for your exam. So this bit here. So if you're writing down notes, that's the bit here. Okay, I'm going to explain it, but the explanation isn't really necessary for the exam, but that is your line you need. Okay, So if I add the metal oxide and add it to water, I'll make a metal hydroxide. Now, as you go down the group, the strength of the alkali produced increase, the pH goes up. Okay? Now, the reason is because and again, this is not assessed, but it does make sense. As you go down the group, the size of the ion gets bigger and bigger and bigger and bigger and bigger. And the bigger the ion, the weaker the ionic bond. It's a very simple thing. If the bigger the ion, the weaker the ionic bond. That means bigger ion, weaker bond between the M and the OH, which means the magnesium hydroxide or calcium hydroxide will dissociate. If it dissociates, then you've got lots of OH minuses in solution, which means you get a stronger alkali. Okay? Whereas if the bond is really strong, the bond doesn't break, and therefore it doesn't solubilize and it doesn't dissociate. Okay? Now that means the pH will go up as you go down the group. Very important to remind you of that. Now, it's a good point also to point out a couple of things that can occur in the exam for 1 mark questions that can be on group 2. First of all, calcium hydroxide is used to increase the pH of soils. So you'll see an example somewhere where they say they put calcium hydroxide. Why are they putting calcium hydroxide on the soil? It's because the pH of the soil is too acidic, and so they add calcium hydroxide onto there, and then that will increase the pH of the soil and bring it up to more around neutral or alkaline. Okay, so unfortunately you do need to know that example. Next one is calcium carbonate or magnesium hydroxide are used as an antacid. So you'll see examples when it goes into your stomach, the calcium carbonate or the magnesium hydroxide react with the acid in your stomach. And if you have an acid plus a carbonate, you get carbon dioxide, which is why you burp. And that's why you burp when you have an antacid, you see, because you're getting rid of the carbon dioxide that is in your stomach. Okay, right. So let's move on to some of the questions now. And these are quite difficult questions, and I've included these because most videos you'll see will not include these type of questions, and these are the ones that are hard. Which metal oxide will give the highest pH when 0.1 gram is reacted with excess hot water to form a solution? So, really important, the excess hot water, okay, and the solution. Both those things together are telling you that all of this is reacted, okay? All of it is reacted. So that means basically if 0.1 is reacted, all of that 0.1 is reacted, okay? So if that is the case, you can work out all of the moles. So I want you to stop the video right now, and I want you to work out all of the moles of all of these. So all you have to do is do 0.1, because it's 0.1 grams, and divide it by the atomic mass in each one. Okay, so I want this video to be not interactive, so you don't just watch me. Stop the video, work out the number of moles. So I'm going to tell you how to work out the number of moles. So the number of moles is just going to be moles equals your mass over your atomic mass of your element. Okay, because you're going to make, and you don't need to do it for the actual atom itself. You can just find out how much of just for the metal, because the oxide is the same all the way through. So basically you just say, well, let's do it for the metal. Or if you want to do it more accurately, you can say moles equals mass divided by MR. If you're doing the MR, you're going to do it with the metal oxide. If you do it for AR, you're going to do it for the mass of the metal. It doesn't really matter because end of the day, it's still going to be in order because the actual answer is affected. Now, if you get that, and if you do that, so hopefully you've done that by now. If I just did it for the metal, and I didn't bother doing it for the metal oxide, I did it for the metal, I would find that the highest number, okay, is going to be B. Okay, so that is going to be B. Because if you work out B, you find that B has the highest number of moles. Remember, it's completely dissolved, which means if it's completely dissolved, it's completely dissociated. And if it's completely dissociated, it forms the highest pH. Now I'm going to go through that one more time, just to make sure from start to finish. You're putting metal oxide into water. It's hot, and it says you form a solution. That means your metal oxide is going to go to 2 plus the O2 plus the OH minus, and it will be 2OH minus, because remember, this reacts with water to make this hydroxide. Okay, so this is going to react with the water to make this hydroxide. Okay, now if it is completely and utterly dissolved, it's completely dissociated. If it is completely dissociated, okay, I just need to know what is the largest amount of moles of each one of these, and that will give me the highest pH, because that will give me the highest amount of this. Okay, so I just want to find out which is the highest number of moles. So all I can do is I can go, right, okay, I can put the metal oxide molecular mass in and work out the number of moles there. Or if I want to do it simpler, the oxide is the same all the way through, so I can use the metal. And I find that the largest number of moles is this one, and it's 4.12. If you use the metal, it's 4.12 times 10 to the minus 2. But it doesn't matter whether you use the metal or the metal oxide. This is the highest amount of moles. If it's the highest amount of moles, that means you've got the highest amount of this, which means you have the highest amount of this, which means you have the highest pH. So our final one is which metal oxide will give the lowest pH. So this time we're going for the lowest pH, more acidic. Okay, and then we go for when 0.1 grams of each is reacting with 50 centimeters cubed of water and a solid remains. So that is telling you, because it says a solid remains, and let's just underline that, okay, because it says a solid remains, okay, and it's giving you a limited amount of water, it means that these are not fully dissolved. So they're not fully dissolved because of that limited amount of water and that limited amount of solid. Now, if that is the case, okay, we look again and we say, right, okay, instead of looking at all of these in terms of working out the moles, we don't have to work out the moles anymore. Because in the last one, it's completely and utterly dissolved, which means it's completely fully dissociated. It means just the largest number of moles is going to be the one that's most dissociated, and therefore is going to be the one with the highest pH, more hydroxide. Okay. If you look at pH here, we're looking for the lowest pH. So we're looking for the lowest pH. So if I'm looking here, I'm going for the one that is the least alkaline. So the least alkaline. So I'm going back to my rule, as in, if you go down the group, what is the least alkaline of these? So if you take the magnesium is at the top of the group and the barium is at the bottom. So it's either going to be B or it's going to be D. So which one of these is the most alkali? Well, it's D, because D has got the weakest ionic bond because it's the biggest radius, as in barium has the biggest radius. So it's the weakest ionic bond, which means it dissociates more when it's added to water. This has the smallest radius, which means its bond is stronger, which means it stays together, which means it doesn't dissociate. Okay, so when that reacts with water and makes magnesium hydroxide, they stay close together, they don't dissociate, which means it's less alkaline. If it's less alkaline, it's going to have the lowest pH. So the answer for this one is B. Now, if you like this video and you think it is very, very helpful, let's just go down here. And you think it's very, very helpful, please could you like and subscribe, do all that normal stuff. But my most important thing and my most plea is share, share, share. I just want as many people as possible to get as much use out of these videos as they possibly can and as much help. Thank you.